All right, so here we're going to talk about trigonometry. And in the introduction to trigonometry, there's a few basic concepts we want to start with first before we build upon that, so that you actually understand what trigonometry and specifically trigonometric functions really are and what they mean. To do that, we start with the concept of the unit circle. So, what is a unit circle? Unit circle, here measured on a Cartesian plane, right, where this is the x-axis and this is the y-axis. Is this shape, circle, and this circle has radius, r, r equals to 1. That is to say, the unit circle is described by this equation, x squared plus y squared equals 1. Because if you remember, the equation of any circle is r squared equals x squared plus y squared. And therefore the radius equals the square root of this in any general circle. If the radius is 1, 1 squared is 1, so we're back to here. And we say the unit circle because all we're going to do with this is, instead of talking about necessarily any generic circle where we have to deal with r, we'll just assume r equal to 1, makes this the simplest it can. And therefore, we can determine things about this circle doing it this way. First thing we want to do is figure out how to find if a point is on the circle. Oh, and do note, the unit circle is not a function. Right? The unit circle very clearly fails the vertical line test. We will find a way to cheat around that and use this concept in functions. For now, it's just a shape. So this starts on page 402, chapter 5. And we're going to look at this point. We're going to say that this is on the unit circle, and we're going to prove it. It's the square root of 3 over 3, square root of 6 over 3. Let me make sure I write it down correctly. And let me make sure it looks vaguely visible. So I want to show that this point is on the unit circle. How do I do that? Well, same way you show any point is on any line, right, or on any figure. You take this ordered pair and plug it in. So I say x squared plus y squared equals 1. Let's see if this point satisfies this condition. So x is the square root of 3 over 3 squared plus the square root of 6 over 3 squared. Does this equal 1? Well, what are these? Just go through it step by step. We say it's the square root of 3 squared over 3 squared which equals 3 over 9 plus 6 square root of 6 squared, 6. 3 squared again is 9 equals 1, and this is 9 over 9 equals 1. So we're good. So I know that this point x equals the square root of 3 divided by 3, y equals the square root of 6 divided by 3, is on the unit circle. Now, if I were to figure out where is this, well, I know x equals the square root of 3 over 3. So the square root of 3 is about 1.7. So this is divided by 3 is approximately 0.6. So we're somewhere in here up to here, right? So maybe right about there is this point. So I'll look at it in my circle, and I can say this is square root of 3 over 3, square root of 6. Somewhere around there. So that will let us determine if a point is on the unit circle. And now we can then determine what other corresponding points are on the unit circle. Right? You can see the unit circle contains points from -1 to 1 in the x direction and -1 to 1 in the y direction. So any point from 0 to 1, or 0 or -1 to 0, as a corresponding point on the unit circle. And you can also see that, in fact, each point on the x or y direction has 2 corresponding points on the unit circle, except for the 4 cardinal points. Here, where we're at -1, 0. Here, we're at 0, -1. Here, we're at 1, 0. And here, we're at 0, 1. Every other point, each x value, right? If I have x equals 0.5, I have 1 here and 1 here. If any y value has 1 on either side, etc. So let's locate a point on the unit circle. Next example, just to show that before we move on. And here I want to deal with the point square root of 3 over 2. So I want to have this point and find y. So what y values can I have for this? Well, take the square root of 3 over 2 squared plus y squared equals 1. I subtract this, so I have y squared equals 1 minus the square root of 3 over 2 squared. And I take the square root of that. Right? But what do I have? This is actually y equals the square root. This is going to be plus or minus square root, right? 1 minus square root of 3 squared is 3. 2 squared is 4. This is the square root 1 over 4, which equals plus or minus f. Sorry about that. So we can say here that the point x is the square root of 3 over 2 has 2 corresponding y coordinates, plus and minus 1. Which, as I said, if we have x is the square root of 3 over 2, which is approximately 0.7, 0.8 over here, it's at y equals 1/2, and y equals negative 1/2 here and here. So now we're going to come to what's called the terminal point, and this is the key of the unit circle and what it means. So what is a terminal point, right? Terminal point is the distance along the unit circle from the x-axis you have to travel. And I'm going to draw it separately. So like I said, here is the unit circle. The terminal point, if you start with the x-axis here, if you start at the point 1, 0, and you move counterclockwise around the unit circle, wherever you stop is the value of t. So what does that tell us? That tells us that the terminal point, t, has a few things. So t is greater than or equal to 0. Right? T starts here and moves around the unit circle. And t is less than or equal 2 pi. Because 2 pi is the total distance around this circle that you can go. Right? So if I start here and I go all the way around, I will have gone around the circumference of this circle once, and the perimeter of the circle, is what we call the circumference, is 2 pi r. Unit circle r is 1. The perimeter of the unit circle And then t could go around again, but now it doesn't really matter, right? If you went around, and this is what one of the examples is. If you start at 0, you go around once, that's 2 pi. Go around twice, that's 4 pi. You're still back at 0. So this tells us that t repeats within this amount. And we can look at example 3 about finding terminal points to get some ideas like this. And that what that says is ways you can look, otherwise ways you can look at t, because you could go around it the opposite direction. So I say this is plus t. I could go this way. I'd be going in if I go clockwise, I'm going in the minus t direction. And if you look at example 3 on page 403, it talks about finding terminal points. And it shows you above what t values are, and then below that in the example, what you would do to deal with these other t values. So if you look at first, we can define some of these points a little more clearly. Right? I can define here as t equals 0. Here is t equals pi over 2. Here, t equals pi. Here is t equals 3 pi over 2. And as we come back around, t equals 2 pi. Now the key here is, once we do that, we start repeating. So if you look at example 3 and it says, where is t equals 3 pi? Well, for t to equal 3 times pi, I would go around once, that's 2. And then around another one, halfway, back to t equals pi. So I know that odd numbers, or odd multiples of pi, return to the same place. I know that even numbers, multiples of pi, return to 0. So if we start thinking of it this way, I can say t of, 2 pi equals 0, equals 4 pi, 6 pi, etc. T equals pi equals 3 pi, 5 pi, etc. And the same thing with pi over 2, right? You can find a relationship here. And with these, if you're going around a quarter of the way, and then another way. So if you go around pi over 2 plus 2 pi, you're back here. So think of it as anytime you go 2 pi, that's a full circumference. That's a full rotation. When you do that, you're returning to that initial point. Basically, you can just simply subtract out any even multiples of pi, get back down to within 0 and 2 pi, and figure out where you are in the unit circle. Now, next in the book, it comes up to something called the reference number. And the reference number, I think, is a complicated concept that we're kind of going to skip because there's a much easier way to think of it that's coming up. The reference number, just in general, tells you how far from the x-axis you are. So if I say, at this point t, this point here, from this part of the x-axis, negative up to t, tells me something about the reference number. We're going to skip that until we get to, I believe, 5.2, where we're going to introduce the trigonometric functions. And then we're going to use those in this idea of the terminal number precisely. So the trigonometric functions, we have a few of them. There are, in fact, 6. We call them the trig functions. And these are useful because they are functions. That's the best part of them. We are using these to cheat our way away from this circle, which is not a function, into something that is a function. So let's look at what they are first. There's the sine, cosine, tangent, and then there are reciprocal or inverse trigonometric functions. There's the cosecant, secant, and the cotangent. Now, the cosecant, these are all defined as reciprocals because this is 1 over the sine. This is 1 over the cosine. This is 1 over tangent. Now, these are not functions in of themselves yet. I have to give them a parameter, right? In the same way that you can't say, you can say f as a function, right? But you need to know what it's a function of. Cosecant, cosine, tangent, these are all functions. But we want them to be functions of something. And to make life easier, we want these to be functions of t. Why? Because t is the distance along the unit circle. And t is the distance along the unit circle tells us something important. It tells us that the sine of t is y, the cosine of t is x, and the tangent of t is y over x. Which means these things are the opposite. Now, with the important caveat, x can't be 0 in the tangent, y can't be 0 in the cotangent, y can't be 0 in the cosecant, and x can't be 0 here for the secant. You can't divide by 0. If you divide by 0, these functions will be undefined, and therefore they will have asymptotes at those locations. So the trig functions are all f of t, right? So that'll be useful. And these all have values. And their values are given by this, which means I'm now going to be able to make ordered pairs out of all of these things. So there's a couple of things that happen right now. And I want to leave, I don't want to erase that yet. It's in my way. So I'm going to erase the unit circle. And we're going to look at example 2, or example 1 actually. And we're going to ask what are the trigonometric functions at these values. So I want t to equal pi over 3 and t to equal pi over 2. Find the 6 trigonometric functions of each real number. So I'm just going to write these down, and then we're going to talk about how to do it. If I say evaluate t equals pi over 3. Well, what does that mean, t equals pi over 3? It means I go from t, 0, and I go around the unit circle until I get to pi over 3. Pi over 3 is less than pi over 2, so it's over here somewhere. And if I want to find the values, I want to find sine pi over 3, cosine of pi over 3, and the tangent. And to find the reciprocal functions, I will just take the reciprocal of them. So for the most part, we only use these when required to. We use these all the time. How do I find the sine of pi over 3? Well, I could try to find it directly, but I know that it's y. So that's the y value. of where we are in the unit circle. And the way you generally find it is with your calculator, and you press the sign key, and then you put pi divided by 3 as the operator. And you might get something that looks like this, which says error, go to syntax. You ask yourself, what happened? Well, what happened could have been you hit the wrong thing, but more importantly, you may be in the wrong mode. I was in the wrong mode. Hard to see on this guy. This is my trusty TI-86. You have to be in radian mode for this to work. Make sure when doing this you're in radian mode, not degree. And the reason for why you have to be in one or the other, I think is the next section. So if I go back, I go sine of pi divided by 3. I get a number. I get 0.866. Okay. If I take the cosine of pi divided by 3, I get 0.5. If I take the tangent, and just by pressing the tangent button, I get 1.73. Which I certainly should get, because of the tangent is y divided by x. 0.866 divided by 0.5, about that. So that's good. That's what I should get. And remember, when using your calculator to always to assess these, always close the parentheses. Because if I were to say that cosine without the parentheses pi divided by 3, I get minus 0.333 repeating. And that's not right. Because what that's doing is it's using the order of operations. So let me just note this. Not the same thing to your calculator. This here, cosine of pi divided by 3. That's what your calculator thinks you're asking it, right? Because it thinks this is one number, cosine of pi, and then you're telling it to divide it by the next number here, 3. You're not telling it to take cosine of pi over 3. Cosine of pi is minus 1. Which makes sense. It's the x value of t at that location. T at pi is x value minus 1. And then you're dividing that by 3. Whereas what I really want to know is what is the x value of t at pi over 3, which is up here, is 1/2. So if you look at these, and as we say, if you look at these and squint, this should look like a logarithm to you. Right? There's a little bit of three things. The sine of t gives you the y coordinate. The log of x is an exponent. It's a number that gives you the exponent you need to raise 10 to. So while log tells us what happens in powers of 10, sine tells us what happens in rotations. Now, mathematically, in the real world, things rotate constantly. Sines, cosines, tangents of angles are all very applicable to engineering and to physics and to all kinds of other. There's plenty of application for them in those disciplines. So logarithm of one variable. So logarithm is a type of function. Logarithm of x is a function. It feeds you some value of y. These are direct functions of x and y. This is an implicit function. The sign of this function gives you the y value at that location. The idea is we are going to combine these ideas, and these ideas mathematically have a lot in common. Which brings us to probably the most important thing, now that I've likened them to logarithms, is to liken these things to angles. So now let me get rid of this section here, and let's draw an angle and see how the three main trig functions line up with it. I don't need that either. So I draw my coordinate system. And now I'm going to draw a triangle. And on that triangle, I'm going to superimpose the unit circle. So now you can look at this and say, what is happening here? Well, on the unit circle, let's say that this is t equals pi over 4. That's approximately where that is, right? This is t equals 0, this is t equals pi over 2. We're kind of in the middle. Not exactly what drawn to scale, but let's say this is the point t equals pi over 4. Well, this is a right triangle. So that's an angle of 90 degrees. There's some angle here. There's another angle up here. And these angles of a triangle have a certain properties according to geometry. And we're going to think about them and exploit them right now. You can see that the value of t on the unit circle corresponds directly to this angle. And that's when I was talking about radian versus degree mode. T is in radians. This angle we could take in degrees. Right, and I want to say, I don't know, let's find the sine of pi over 4. So I can say a few things about this. I'm going to write them down. I can say sine pi over 4 equals 7.07, I believe. 0.707 approximately. What's the cosine? And the cosine of pi over 4 is 0.707. Now, if I were to think of this in degrees, so a circle is 2 pi distance. We also can say it's 360 degrees, right? So we can say that 2 pi equals 360 degrees, or pi is 180 degrees. So pi over 4, right? So pi over 2 is 90. And pi over 4 is 45 degrees. So this here is an angle of 45 degrees. It is a terminal value of pi over 4. And that's what we say when we need to have degree mode versus radian mode. And make sure you feed it the right number. if you change the mode on a calculator, you can tell it to give you, I could say, switch my mode from radian to degree. So I switch back to degree, exit out of that. I say sine 45. Sine 45. I think you should be able to see just a little bit that sine of 45 degrees is 0.707. Meaning I can relate the angle and the terminal point in this way. So the terminal point is literally just an angle made with the x-axis given in this form as a fraction of pi over 2, some multiple of 2 pi to go around the circle. Instead of telling you what degree you're in. And there's this relationship, there's a graphic, another one on page 411, where it talks about how you turn these things into useful information, right? And we have an angle. This angle has an opposite side. It has an adjacent side. It has a hypotenuse. And there is a way to relate these directly. We're talking about the values and more trigonometric functions, which we'll get into more in the next lecture, where I talk about the fundamental identities of trig functions and more on what to go here. So this is the unit circle as it relates to the angle. And keep these ideas of opposite, adjacent, and hypotenuse in mind going forward. Thanks for watching, and we'll hear from you next time.